Okay, so we're going to continue talking about air pollution and ways of modeling that today. Remember that last time in class we talked about figuring out the indoor air pollution concentration, and today we'll be focusing on a model that describes how air pollution disperses outside. So your related homework assignment is due before class on Monday. That's homework 12. You should submit that on Blackboard. And we'll do an in-class exercise today that covers the Gaussian dispersion model that is probably the trickiest part of the assignment you've got due on Monday. So, any questions about the announcements? So, air pollution can be minimized. You know, preventing it before it occurs is probably the best approach. And ways of doing that would be cars and engines that don't use as much fuel for the miles that they're traveled, or switching from incineration to other ways of disposing of things like sludge or solid waste. You know, there are places where they incinerate garbage rather than landfilling it. And there are a handful of places where land space is really rare and valuable, and maybe where it makes sense to incinerate waste. But if done appropriately, like with clay liners and leachate collection systems, there's actually nothing so terrible about sanitary landfills. It's actually an environmentally sustainable way of disposing of solid waste if it's correctly contained, and so probably better for the environment than burning garbage. So we can minimize air pollution by just getting less stuff burning. We can try and improve the way of straining the pollution out before it gets into the environment. So that is, still have gasoline engines but add things like catalytic converters, or still have industrial processes that may generate particulates but add emission control devices like what's pictured here, an electrostatic precipitator. So we'll talk more about those different types of prevention and removal efforts today after we discuss the Gaussian dispersion model. But more often than not, even after both of these, there's going to be some pollution that gets into the environment. So we need to have a way of predicting what the concentration of pollution is going to be at any particular location. Because air pollution, ultimately, there's going to be some that's emitted and that disperses into the environment. And what we're hoping is that the concentration gets lower and lower as it spreads out over a larger area, as the polluted air is diluted with fresh air. And so that's what the model we're going to talk about today describes, is how polluted air diffuses. So diffusion is just a process by which high concentration particles will naturally tend towards filling the void of concentration. So diffusion happens in fluids, both liquids and gases. So that if I opened a tear gas canister in the corner of the room, eventually it would fill the whole room. Even without a fan running, just the random movement of particles would cause the pollution to spread out and fill the entire classroom. So diffusion is an important process. In addition to diffusion, though, there's what's called advection, which is the bulk mixing due to things like wind. So the diffusion component of it, we're going to be looking at the probability distribution. And if we're polluting air using a smokestack, for example, you'd expect, just kind of instinctively, you probably understand that the further downwind you go, the more spread out width and height that pollutant is. And we're going to use a standard distribution to estimate the width of the plume and the probability that a given particle is transported either to the side of the central axis of the plume or vertically. The bell curve actually is going to be applied to both of them. So here we've got a smokestack, and what we're showing is that when the hot exhaust gases come out of a smokestack that has a height h, those hot gases will continue to rise as they're cooling off. So delta H is the distance that the smokestack gases rise beyond the physical height of the smokestack, where H, capital H here, is the effective stack height. And the effective stack height takes into account the physical height of the stack and also how high the hot gases are going to rise. Eventually, when they stop rising, then it's just horizontal movement and vertical movement due to dispersion at that point. So here you can kind of get a sense for what we're talking about with this bell curve vertical and bell curve horizontal. What we're saying is that if you're on this central axis of the pollutant plume, the concentration is going to be the highest. And I think that probably makes sense to you that, like if you're in the middle of the smoke, the concentration is greater than if you're at the edge, where fewer of the particles, probabilistically speaking, will have both diffused down and to the side, given a certain distance downwind. So the variables that we're going to be keeping track of in this Gaussian dispersion model, we want to know things like how hot is the exhaust that's coming out of the smokestack? How tall is the smokestack? We'll be interested in things like what's the wind speed? We'll be interested in what are the atmospheric conditions? Is it sunny conditions? Is it cloudy conditions? Is it daytime? Is it nighttime? Because all of those factors are going to influence how spread out that standard distribution is. So we want to know at a certain distance downwind of the stack, maybe if we're 2 kilometers downwind, and rather than being immediately downwind, maybe we're also laterally some distance away from the center line of the plume. We want to be able to predict a distance downwind and then a distance laterally away from the central axis. What is the concentration of pollutants there when we know the emission rate? So the emission rate is, grams per second or kilograms per day. It's some representation of mass per time of the pollutant that's going into the atmosphere, and then we take all of the other physical characteristics we know, like the gas temperature, the stack height, the wind speed, and so on, and use that to estimate what the pollution concentration is going to be. So any questions so far about the theory of the Gaussian dispersion model? So let's talk a little bit more about atmospheric conditions, because that's part of it. Whether the plume is going to be looping, or whether the plume spreads out like a fan, or maybe if there's an inversion, that could cause kind of like a hard cap that the pollution's not able to disperse above. So the things that we're interested to know about would be wind speed and thermal effects. So during the daytime, there may be thermals where the solar radiation heats the ground surface, and then that warm air that's adjacent to the ground surface will then rise. Whereas that's not going to happen at night. So night conditions are more stable with less dispersion due to solar thermal effects. And what the Gaussian dispersion model generally does to understand the effects of atmospheric stability is to try and classify conditions on a letter basis, where A is associated with unstable conditions, meaning the pollution will spread out more if we've got stability class A, and stability class F, stable conditions, means that generally speaking the pollution is going to stay together more. So let's compare, for example, for a certain wind speed, the effect of solar radiation. So if the wind speed is between 2 and 3 meters per second, we've got strong solar radiation, then that's going to be unstable and the pollution is going to spread out more. So if we have like a lot of heating at the ground surface and the air is rising and the thermals are kind of causing a lot of vertical turbulence, then that's going to tend towards unstable conditions and the pollution spreading out. Whereas if we have slight solar radiation, maybe because it's winter time, and the sun is low on the horizon in the wintertime, the radiation isn't as intense. Or if it's a cloudy day, then there'd be less solar radiation. And so conditions are more stable with less solar radiation. And then if you look at night, when there's no solar radiation, then the stability classes tend towards even more stable conditions, where the pollution is not going to disperse as much. And then, as you'll see, as the wind speed changes, then that also has an effect on what's happening. And it's a little bit counterintuitive. Like I'm saying that F is the pollution is staying together, but the wind speed higher is for the letters that are closer to F. So the way to understand that is just that if the wind is blowing quickly, then the pollution stays together before it has time to spread out. Like that is, it's getting further downwind before it expands. Whereas if the wind is very slow, then it's expanding quickly, for the amount of time it takes to get from one point to the other. So our book has this figure. It's a nomograph where you can look up for a given distance downwind and then the different stability categories, how much you should use as the standard deviation. This is horizontal dispersion. And you'll notice it has here the units of meters. And so like if we were doing this model for a distance 2 kilometers downwind, you'd go up from the horizontal axis and you'd reflect it off of whatever your stability category was. Maybe if it was category E, then you'd go over, and in the case of category E, 100 meters is the horizontal dispersion. And so we've got figures for both horizontal and vertical dispersion, where you basically have just classified A, B, C, D, depending on whether it's day or night, the amount of solar radiation, and the wind speed. Those are the factors that determine the stability category. Once you know the stability category, you either go to this figure to look up S sub Y and S sub Z, or there's equations. I think in the homework I ask you to use these equations rather than the figures. It's a little bit more precise. These are the coefficients that those figures are built from. It's just a regression equation that relates the dispersion with the distance. So x is the distance. Either you can see there's different coefficients that you'd use if x is less than a kilometer compared to more than a kilometer. And then the coefficients would tell you in meters what is the horizontal and vertical dispersion. Okay, we also have a formula that allows us to calculate how much the plume rises. Remember, the exhaust that comes out of a smokestack is generally much warmer than the surrounding air. And so if it's warmer, it's going to rise. And the question is, how quickly is it going to cool off? And that's what this tries to estimate. It looks at the velocity of the plume as it's coming up. So here, V sub s, the stack velocity, that's talking about the velocity of the gases as they're going up. It looks at the difference in temperature of the exhaust and the ambient air, the diameter, meaning like assuming, for example, a circular diameter of the smokestack. So D is just the hole at the top of the smokestack, and then U is the wind speed. So this is just an empirical equation that gives us an idea of the plume rise distance, where we know the overall effective stack height takes the physical stack height and the plume rise into account. And now we bring it all together with this gem. This is a big complicated equation, but what it has is the rate of emission, E, so that's the number of kilograms per hour, mass per time of the mass that's being burned, or it could be a gaseous pollutant, particulate. It's just physically how much is being discharged by the stack. And you'll notice that there's a couple of places where we use these standard deviation for the plumes horizontally and vertically. Both here just under the emission rate, but then also in these exponential functions. The purpose of the exponential functions is to take into account the location of the point where you're actually doing the sampling. So see here what it's saying is there's the central axis that the plume is going downwind from, but then you may not be on that central axis. And so here y, the distance y, is the distance between this point and here. So it's how many meters off the central axis of the plume that you are. And this equation would give you the concentration at ground level. Okay, so I've printed out this in-class exercise. Let me give you this one. What we're trying to do is practice using this Gaussian dispersion model to find out, first of all, step by step, how high the smokestack gases are going to rise in the atmosphere. So we want to know the plume rise, and then we want to determine the effective stack height, and then classify the atmospheric stability and find out the standard deviations. Okay, so on the handout it says part A is find the effective stack height. So you're going to have to use delta H, and then just reading the problem statement we can see that lowercase h is 90 meters. So the first thing is calculate delta H. And if we go back to the notes, let's check the units for this formula delta H. So temperature should be in Kelvin. So the problem statement I've given you, the temperatures are in Celsius. So you need to convert that to Kelvin. And then the other thing is the units of pressure here. P is pressure in kilopascals. And so that's what I've already given you. So I guess maybe for using this formula, the first thing to be aware of is temperatures are Kelvin. And the conversion here it is at the bottom. It's Kelvin is 273 plus Celsius. So let me pause. Feel free, of course, to collaborate with your classmates, double check your calculations, make sure that they got the same thing as you, all that. And ultimately what we want to know is what is the concentration downwind, but I've broken it up into step by step where we're going to start off by finding out the effective stack height and then the horizontal and vertical standard deviations. Okay, so let's just check in and make sure that we're all on the same page with the effective stack height. So you can see I've labeled some of the variables here. So h, lowercase h, the physical stack height is 90 meters. U is the wind speed, that's 5.5. X, the distance downwind is 4 kilometers. We are going to eventually need this 500 meter distance, the distance from the center line. That's what we're going to use as y. I guess I should have labeled that. Y is 500. E, the emission rate, 2,200 grams per second. Stack diameter D, 0.75. exit velocity 11.5. So we've got the temperatures, air pressure, and so on. So as I was circulating around, I noticed it seemed like everybody had no trouble finding the temperatures in Kelvin. So the gases that exit the stack are at 748, whereas the surrounding air is 288. And it's partly that big temperature differential that drives the plume higher after it comes out of the physical height of the stack. So delta H, that additional rise, is 4.31 meters, which means the effective stack height's 94.31 meters. So all of that just to find out where the pollution plume starts at. That's, we're saying that it begins its Gaussian dispersion at a height of 94.3. So we assume we're at the ground level. That's what we care about, is where people are breathing. So we're going to be at the ground. The pollution plume, it is an elevation of 94.31, and it's going downwind and it's starting to spread out and get bigger and bigger. So the first step to understanding how quickly it spreads out vertically and horizontally is by looking up these standard deviations for horizontal and vertical based on the stability class. So I diagnosed the stability class as being stability class C because in the problem statement it says that, let's see, very sunny. So if it says very sunny, we can assume the incoming solar radiation is strong. And then we had, it said that the wind speed was 5.5 meters per second. So that's right in the middle of the 5 to 6 meters per second range. So strong, it's daytime. I guess it wouldn't be very sunny if it was at night, right? The problem didn't specifically say it's daytime, but I'm just going out on a limb. So stability class C. And it's from that stability class that then we could get all of these coefficients for finding the horizontal and vertical standard deviations. So I'll pause again for a moment, allow you to calculate what is S sub Y, what is S sub Z. And if you've already got it, you can flip the page over and start working on the Gaussian dispersion model. Figure out, basically we want to know what's going to be the concentration downwind. I got a good question on why is it that we're getting meters in this equation when we put kilometers in for x. And this is not a dimensionally homogeneous equation. There's nothing fundamental about it. Like what we're doing is we're taking kilometers to the power of 0.894, multiplying it by some unitless coefficient, and meters is coming out. It's just observational data has been gathered out in the world, and they came up with a best fit curve. So yeah, we do get meters. This is, when it talks about standard deviation S, that is how far from the center line the concentration is down to 64%. Like if you think about what the area under the curve means, one standard deviation on either side of the center line represents 64% of the area under the curve. So Y is 500, and I've got the substitutions that I did into here if you want to double check it. You'll notice I'm pretty meticulous when it comes to putting the units in. I think that's a good habit. I've mentioned it before that you'll avoid making mistakes oftentimes if you've got the right units into the formula, just to remind you of what it is. And so I'll give you a moment to copy this down or to finish your calculations, but what we should see is about 566 micrograms per cubic meter. So this first term tells you what's the concentration at the center line of the plume. And then what these two exponential functions do is they account for how much dispersion has occurred and what is your location, both vertically and horizontally. So this 0.3791 is where it took into account that we're 500 meters away from center line. So what that's saying is that you reduce the concentration to 37.91% of center line if you were off to the side. And then this term accounts for how far down below the center line we are vertical-wise, elevation-wise. So each of these multipliers just basically corrects for our location relative to the center line of the plume. So if we just wanted to send a drone up and measure the concentration of the pollution right in the center line of the plume, then this first term is what we could use to simulate that, and maybe the drone would be able to measure it directly. But then these two secondary terms just correct for our position. Does anybody have questions about this illustration? All right. I think you should be good to go on the homework assignment with this example. But let's talk more about how air pollution is controlled. You know, the formula is a little bit different if there's an inversion aloft. Like if there's a hard cap that the pollution can't rise any higher, then there's a different model for trying to calculate what the pollution concentration will be. Basically, it only spreads out side to side once the smoke rises to the height of an inversion. So we won't do an example, but there's just a certain point where you can see it reaches the inversion layer and then is fumigating the air below the inversion. But air pollution control is really important because, as I mentioned at the beginning of the lecture, inevitably there's going to be some stuff that we're not able to reduce the pollution or kind of mitigate its effects. There's going to be stuff getting into the environment. But how can we reduce what is discharged? Well, it depends on the nature of the pollutant. Some air pollution is gaseous. Some air pollution is particulate. So particulate meaning like PM10, PM2.5, or we talked in a prior class that that's referring to the diameter of the particle in microns. And what makes it dangerous is that it can get deep into your lungs, that it's not filtered out by like the little hairs in your nose, are actually pretty good at getting dust. But PM2.5, PM10 is going to get into your lungs. It's not filtered out. It's not stuck on your throat. So one of the ways that we can prevent dust from getting into the atmosphere is with a bag filter. And if you've ever owned and operated a vacuum before, probably a bag filter makes perfect sense to you. Have you ever noticed that vacuum bags, they're made out of kind of like a porous, I guess, fabric, for lack of a better word. It's maybe like a paper that has very small holes in it, and what your vacuum does is it's agitating the carpet with a brush, and then it's using suction to suck the dust that has been shaken loose by the brush, and it's sending it on the other side of the blower. The air is discharged into a bag, and so the air goes through the bag and the dust stays in the bag, and that's basically just scaled up at an industrial size. Particulate control can be affected through bag filters, where dirty air comes in, goes through some sort of a fabric, and occasionally the fabric has to be shaken out or disposed of, but it just through the mechanism of both filtering, but then also sometimes electrostatic attraction. Has anybody here ever changed the filter in your furnace before? If you've changed the furnace filter, you'll notice that dust gets stuck on that. It's actually pretty satisfying when it's really dusty to throw it away and put the clean one in. But they kind of do a similar thing with furnace filters where they have charged particles that you're trying to trap, and so those charged particles are attracted to the fabric filter, and so it's not just screening, it's not just physical screening, but it's also electrostatic attraction. So it can be a combination, but particulate control is one of the mechanisms that's used, and it works on a wide range of particle sizes, so it's effective in that sense. But it's filtration and then surface forces, meaning attraction, because small dust particles have a negative charge. The bag is either neutrally charged or positively charged, and so it's attracted to stick onto the surface. Another way to clean out particulates is to spray water into the smoke. And if you've got dirty air coming in and it's going up a smokestack and you're spraying water in there, then the vapor or maybe the little droplets of water are able to cleanse the air as the air is going up. Just in the same way that, you know, on a dusty day after a rainstorm, the sky is more clear. This is trying to basically do that same thing using like an industrial engineered process. So the disadvantage, though, is that whatever it is you're trying to trap now is in water. So you've got some dirty, polluted water. And if it's just dust that can settle out of the water, then maybe no problem. But if it is a toxic dust that you're trying to, or a toxic material of some sort, then you've got a contaminated water that's maybe more difficult to dispose of. So the particles get entrapped in the water droplets. They become heavier. They're going to fall to the bottom where previously they might have been light enough just to go out. Sometimes people will mistake a spray filter for smoke. Like they'll see white stuff coming out of a smokestack and automatically be worried about that when it might just be water vapor. And so it can be unsightly, despite it only being water vapor. People don't like seeing things coming out of smokestacks. It makes them feel uneasy. The big disadvantage really, though, from a practical standpoint, is that the liquid waste has to be disposed of. Electrostatic precipitators are an interesting technology where they're just using charged plates and sending gas with particles through in between charged plates. And some of the plates, they're just literally like metal plates, will be at the end of a positive electrode, some will be at a negative electrode, and the dust that comes in is attracted to the plates. It would be attracted to the positively charged plates. Occasionally they can switch the charge off, wipe the dust off of the plates, and so there's no moving parts, no bags that have to be replaced. So it's a pretty low maintenance kind of a technology, just that occasionally the plates need to be cleaned off. So all of the processes we've been talking about so far are mainly focusing on removing particulate pollution. And the same is true for cyclones. Cyclones, what it is that the gas, the exhaust gas that has the particulates would come in and would be forced in a circular direction that causes centripetal forces that, because the dust is going in a circle, the particles would go to the edge of the cyclone, they'd settle down to the bottom of it and be removed. So it's not as effective as bag filters or electrostatic precipitators, but in this case, there's literally no moving parts, no electricity being consumed. You're just basically making use of physics and the fact that what it's basically doing is getting the dust to settle. And if you have the dust and you stop it, the particles will settle down. But this is enhancing the acceleration. Instead of just relying on gravitational acceleration, if it's going in a circle, then that induces a centripetal acceleration that forces the dust particles to the edge of the cyclone. So hopefully by doing that, you'll get the heavier of the particles to migrate to the outer wall and they can be removed. Skip over that. here is a figure that compares the efficiency of different types of technologies. And so what you want is a high removal efficiency. So if you look at what is the least effective thing, it's just a settling chamber. That is, you take the air pollution that has dust in it and you give it like a big room where the air just stops for a little while, kind of like a grit chamber. Remember when we were at the wastewater treatment plant? A grit chamber is just a wide spot in the pipe where the heavy particles settle downward. So it only works for the largest particles. Here on the horizontal axis of this figure, it's showing that a settling chamber is good for the large particle sizes, very large particles, it'll settle. But if we want to have really effective removal of small diameter particles, then a bag filter, G, is the most efficient for getting those smallest particles out. And it's the one that's you're going to require the most amount of maintenance and is probably the most costly. So you're always paying for performance. Wet scrubbers are used in the similar way. Spraying water into a pollutant plume can not only remove dust, but it also may be effective at removing gaseous pollutants. So if you have like sulfur that has been combusted in coal and it gets up into the atmosphere, it's going to turn into acid rain. The sulfur dioxide is going to combine with moisture in the atmosphere, and it's going to be rain that has a low pH. But instead of letting it out, what if we just sprayed water into the exhaust from that coal-fired power plant? So we kind of force the acid rain to occur in a controlled location rather than letting it get out into the atmosphere. So that's the idea behind a wet scrubber, and they may even add things to the water that can neutralize the pollutants. So if they add lime, which is basic, calcium oxide, then not only are you removing the sulfur dioxide, which turns into sulfuric acid when it's combined with water, not only are you removing it, but you're neutralizing it. So that's one way of dealing with gaseous pollutants, is spraying water into the gas waste stream. Another is to use the process of adsorption, which is just that when there's organic chemicals in the air that's being discharged, that those organic chemicals are attracted to the carbon in coal. And medical marijuana is becoming legal in a lot of states, and some of them do have regulations that control the emission of air from the indoor grow places, and some of them don't. If you ever drive through Denver, between the airport and downtown, you go through kind of an industrial part of town, and you just start smelling weed from the freeway. You'll be driving on the freeway at 70 miles an hour, and it is thick and dank, and you can really smell it. But then I've been to other places that have medical marijuana, and it's an indoor grow area, and you don't smell anything because they are putting activated carbon on the exhaust from the place. And so it's just, the terpenes and whatever that are in marijuana are attracted to the carbon and activated carbon. So it's just similar to removing organic chemicals from water. We can use activated carbon to remove chemicals from air. And that's what's in a gas mask. The way that you remove pollutants like phosgene and other gaseous chemicals that are used for chemical warfare with the gas mask is to have activated carbon in there. Another way we can get rid of gaseous pollutants is just by burning if it's flammable. So sometimes we'll have to use catalysts to try and make it a clean burn, but flaring you'll see often at refineries where they've got a certain waste stream, and it's actually better for the environment. For example, if there's leftover methane, methane is a much more potent greenhouse gas chemical than carbon dioxide. So sometimes there is leftover methane, and it would be better to just burn it than to let the methane go itself out into the atmosphere. So that may be what we're seeing here, is flaring of leftover hydrocarbons that, it's not good to have uncontrolled combustion, but it's better than allowing for the discharge of whatever that is. All right, we're out of time for today. Remember that the homework assignment you're working on is due on Monday. Should be submitted to Blackboard before class. And if you've got any questions, let me know.